Okay, let's see how we can find our K2. Here, let me write y of s one more time here. So our y of s has some partial fractions. Some of them are in our response because of our transfer function, and some of them, like K2 over s minus j omega and K2 conjugate over s plus j omega, are in our response because of our input. Now, I don't care about the rest of them. I want to know how I can find this K2, which is very important for me, because this K2 can show me later how the steady state response of this system to the sinusoidal input is going to be. What I'm going to do in order to find K2, I have to multiply my y of s by the denominator of the coefficient that I'm looking for, which is s minus j omega, and then I have to evaluate everything at the root here, which is j omega. Okay, you know what is y of s? Y of s is basically h of s multiplied by x of s, and then finally I have to multiply it by s minus j omega, and at the end whatever is left here needs to be evaluated at j omega. Let's focus on this x of s. What is x of s? X of s is the Laplace transform of x of t, which was a cosine of omega t, and its Laplace transform, which is x of s, is equal to a cosine of theta multiplied by s minus a sine of theta multiplied by omega divided by s minus j omega multiplied by s plus j omega. This is what I showed you in previous lecture. Now, if I multiply this x of s by s minus j omega that I have here, this s minus j omega will cancel out s minus j omega in denominator here. So what I'm going to have at the end here is going to be h of s multiplied by whatever is left here, which is a cosine of theta multiplied by s minus a sine of theta multiplied by omega divided by s plus j omega, and then I have to evaluate everything at j omega. Okay, now I'm going to simplify everything. So I have to evaluate everything at j omega, which means I have to evaluate h of s at j omega, and I have to replace s here by j omega and the s here by j omega. So let's see what I'm going to have at the end. Here I'm going to have h at j omega multiplied by, in denominator I'm going to have 2j omega, and in numerator I'm going to have aj omega multiplied by cosine of theta minus a omega multiplied by sine of theta. I'm going to write it here. So I'm going to have 2j omega in denominator, and then a multiplied by omega j cosine of theta minus omega sine of theta. Now what I can do is that I can cancel out this omega from both numerator and denominator, and then I'm going to have h of j omega multiplied by, I will bring this j into numerator, and it will be minus j multiplied by j cosine of theta minus sine of theta. And in denominator I have 2. Let's distribute this j over this parenthesis. So it will be h of j omega multiplied by a multiplied by minus j multiplied by j is going to be 1. So cosine of theta, and minus j multiplied by minus is going to be plus j sine of theta divided by 2. Now something interesting here is that this cosine of theta plus j sine of theta is equal to 1 with an angle of theta. So what I can write at the end as K2 is equal to h at j omega multiplied by a with an angle of theta divided by 2. This is an interesting conclusion here, that in order to find K2, what you have to do is that you have to evaluate your transfer function at j multiplied by your input source frequency, and then multiply the result of this evaluation by the magnitude with an angle of theta, which is the phasor of your input source, divided by 2. So this is how you can find your K2. Okay, let's go back to the previous slide. So when we have K2, we want to ignore the rest of them. So now that I know what is my K2, I can do the Laplace inverse of this term. So I know that K2 is equal to h of j omega multiplied by a with an angle of theta divided by 2. Okay, now what I'm going to do is that I can do the Laplace inverse of only these two partial fractions, and I can throw away the rest of them. So I'm not going to even bother myself by calculating the Laplace transform of those other partial fractions than these two, because I know that these two will make my steady state response, and the rest of them will be only transient response. So if I'm interested in transient response, I can include them, but because I'm only looking for a steady state response, I'm going to consider only the first two partial fractions, which are the result of the roots of my input Laplace transform. Now let's do the Laplace inverse. For the Laplace inverse, you know that your y of t, remember that this y of t, because it doesn't correspond to the whole total response, it is only a steady state response. So you have to include this double s here to show that you're looking at your steady state response, not your total response. It's going to be equal to 2 multiplied by the magnitude of K2 multiplied by cosine of omega t plus the angle of K2. Now let me simplify what I have here a little bit more. So what is this magnitude of K2? K2 itself is h of j omega multiplied by a over 2 with an angle of theta. So its magnitude is equal to the magnitude of h of j omega multiplied by a over 2. And then its angle is equal to the angle of h of j omega plus theta that I have here. Now I can describe my steady state response as these two cancel out here. So I can describe it as a multiplied by the magnitude of h at j omega multiplied by cosine of omega t plus theta plus the angle of h of j omega. So let's look at what I have here as my conclusion. This is a very important conclusion. So here I'm looking at my steady state response to a sinusoidal input. What was my input? My input was a cosine of omega t plus theta. So this was my input. As you can see, my input has a frequency equal to omega and then a magnitude equal to a with a phase angle equal to theta. So what I have to do in order to find the steady state response of my output when the input is a sinusoidal, first I have to evaluate the transfer function of my circuit at j omega, in which omega is the frequency of my input, and then I have to use its magnitude here and its angle for my cosine angle, and also I have to use input magnitude and input phase angle. So basically, I can redescribe this in this form. The phasor of my output, let's call it this way. So this is my output phasor. So my phasor, output phasor, is equal to the phasor of h of j omega multiplied by the phasor of input, which is a with an angle of theta. So this is input phasor. So now I can tell you the steps, and then I'm going to show you an example to how, in order to see how we can follow this step. So the first step, in order to find the steady state response to sinusoidal input, is that you have to evaluate your transfer function, which is h of s at j omega. The answer is going to be a complex number. Try to show this complex number in polar form. Then multiply your h of j omega by input phasor. So calculate your h of j omega, then multiply that by your input phasor, and finally your output phasor. You have your output phasor. So the last step is that you have to apply a phasor inverse transform to find the steady state response of your circuit to a sinusoidal input. So these are 3 steps that you have to follow, and I'm going to show you these 3 steps in an example in next lecture.